Right, so this is an attempt. It was actually me who dragged Vilda here, and I'm very grateful that he came along. This was an attempt to understand a little more about what's happening inside of a container. Let me just, you're in the...
I'm blocking, sorry.
So a little bit about us. I'm Naďa. I work in Microsoft currently, but Vilda and we used to work together in a startup called Apiary. And then Oracle, we became friends. He became my mentor. So I'm very grateful that he's here. And yeah, this is a little bit about me. I'm currently working in the Defender Kubernetes platform team in Microsoft, and we run several hundred AKS clusters. So containers are definitely part of my life, but thanks to this talk, it was a little bit selfish of me. Thanks to this talk, I understand a little more about what's actually happening inside.
Hello. Oh, sorry. So I'm Vilda. I'm working in Purestorage. There's a lot of people from Purestorage I see. So hey, we started together in Apiary like, I don't know, 10 years ago or so. I've been doing some development for the last 25 years. I started with Go when it was before version 1 because I was looking for something that's better than C++ for writing services. And this is kind of like a joint talk where I want to introduce the basics, how you start, and then Naďa will take off. Also, the other thing is that there is Naďa, who's very famous in the Go community, right? And we together have a podcast, and I was asked to actually promote it. So there is. You build it, you run it. It's about how you run services and what you need to do. Cool. So let's get started, right? Like this was our first experience with containers. Definitely mine. I was like, yeah, this is cool. I'm gonna do X, Y, Z, and then like nothing worked for a long, long time, right? I guess there was your experience too. I actually have the same experience still sometimes. When I start debugging details in Kubernetes, it's like this.
Yep. Again,
I don't know what's happening. So in order to understand better, it's good to understand what is a Linux container actually. The answer, does anybody like not know what it is? Because it actually is only a process, nothing else. There's no magic. Well, there is a little bit of magic, and that's actually that there is some tricks how to, for the process running inside, the thing that it actually has is a very special thing that is on its own or somehow contained, sorry. Right, it's using like operating system level virtualization, unlike virtual machines where you're basically simulating the whole computer, right? Cool. So for that, you need an operating system, right? In order to have operating system virtualization, you have to have an operating system. So I'm thinking like, does everybody know what an operating system is? Right, there's a lot of things in it. But essentially, like this is how most of the things work these days, right? You as a user or a human, you don't interact with the operating system. It's applications, and they can like use operating system as an abstraction layer for hardware, right? And a lot of the things that the operating system does is, for example, it allocates resources. So it's like your program does not eat all the resources in the computer, meaning like spins the CPU forever 100%, right? That would be useless. Or memory, or other things. So there is some isolation already. It also helps you with access to devices. How many people here are actually writing drivers for hardware? None, yeah. You're using operating system for that, right? Cool. Access to file system, like I guess again, nobody's writing a file system here, so to store stuff, right? You're using, again, the operating system. It does a lot of things, like isolating processes. That's part of the containers. Also, inter-process communication, which I think most people don't know that they use it, but they use it. Whenever you do pipe in the shell, you're using it. And also, like anything in network, right? So, and the important part of operating system is something that's called kernel. I guess like everybody knows this. especially if you're using Linux, this is probably the most famous kernel these days. It's definitely the most used one. Especially like all the Android phones are that, so that's basically the majority of the devices. I guess even like the TVs these days. So now the kernel does a lot of things, and it makes sure that things stick. So for example, if you start typing on a keyboard, that's where the kernel gets engaged and runs some routines that actually go and handle the hardware interrupt and so on. And then you see the printed thing on the terminal. All right. So now, in order to communicate with the kernel, you need to somehow invoke it. For that, there's a thing called system call. This is the Wikipedia definition. It's very detailed, but it basically means there is some way how you make sure that your application, your program can interact with the operating system, invoke some of the functions. And there are rules around it, like how this gets done and so on. So that's a fundamental piece of containers. Without that, there's no containers, right? There's basically no operating system. All the operating systems have system calls. So, how many of you have actually used the system call? I guess like you feel like plenty. And I guess like everyone, right? Either you know or you don't know, unintentionally or intentionally, but you're doing it all the time. So, how many systems calls you think is in this? Is it like 1, 10, or 100? For 1? So everybody thinks it's more than 1. Okay. 10? Is it okay? A few hands. What about 100? Yeah, a few hands. Like okay. Let's see later. So, but let's look at like how Go actually uses this, right? Like how Go invokes system calls and how it kind of like ties together. Because there's definitely you'll have a path for one, the print line that definitely does something, right? So. Like now, diving deep into the source code of Go, I think it's a very useful exercise. So this is in source code fmt print Go. There's this little section, print line, that actually calls, if you look at it, print line calls fprint line is something on like some writer, and there's some write to the buffer. Cool. So far, no system call, everything is just a pure library. Okay, now, std out, it's a writer, and this is the write function. Right, if you go os, file go, that's what you see. And there's this fwrite, file write, and that goes to, eventually, to a function that looks like this. And there's finally some call like called syscall. Hey, finally there. Actually, it's more complicated, but there's a lot of layers of abstraction because Go has to support many operating systems and they're not the same, so it takes a bit of time, but there's this syscall Linux AMD, this is my machine. If you have some other thing, you'll find a different one. And it actually generated, right? Now it's obviously unsafe because you're now reaching to operating system, so you're passing pointers. How many people are like familiar with what a pointer is? Okay, cool. You don't have to worry too much. So, and then the syscall, that's actually a very generic function where the first argument is like, what syscall you want to call, and then the arguments. Here it's like unsigned pointers, unsafe stuff. You shouldn't be writing that very often. Cool. So now how the syscall is actually made then? Right? Because that's like, it goes somewhere, and somehow it happens, and it's not going to be a Go code anymore. So, how many people are familiar like how CPUs work? Like, right, there's a thing called registers. That's the memory part, right? That's like where you can store. It's like memory, or variables, but they are directly on the chip, so they're super fast. There's this ALU. That's actually the unit that does the computation, and there's the control unit that fetches stuff from memory, copies stuff around, and so on, and then executes, right? And so on. Cool, so in order for all this to work, somehow there are rules on like certain things need to go registers, blah, blah. Cool. So on Linux, I'm going to talk about Linux because we're doing Linux containers. If we did Windows containers, if such thing exists, it would look different. But there's a table that says on AX, that's one of the registers, you put a number that tells you what the system provides you, was the system call name, or sorry, the function, and then you have other registers, you put arguments. It's like calling a function, but you have to put it in specific places, and then you do something and it happens. Cool. So now, this is version Go 16 and older. That's how it looked. This was the implementation of the syscall function. So when you're invoking this is assembly and tells you, oh, like this line here, the AX is like, yeah, you put the number there. That's actually the first argument, and then the other arguments are put in order. And then there is a thing called syscall. That's actually a instruction on the CPU, and that actually triggers this thing. And it then the code actually moves to the kernel. That's the stuff that happens. And you come back, and then you have the error handling, the CMPQ, like comparing, checking if error, if not, if yes, so on. Now it looks a little different. Now current version is slightly different, and that's because a lot of the things change in this inside of Go, how actually Go calls functions, put stuff in. Now, if you go current implementation, the AX is already full, because Go nowadays also uses that, so that's cool. So, a lot of stuff. If you want to call a syscall, this is the way to do it, not the previous one. That's kind of like details. Eventually you get there. There's a package called Unix, Golang Axis Unix, that actually provides this wrapper around syscall, so you can run syscalls if you want. Whatever syscall you want, you can do it this way, and you'll be cool. Right? Not all of the syscalls, if I recall correctly, all the syscalls from Linux, for example, are implemented in Go easily. Like so there are some which are not obscure ones probably. Right? So now, when you get to the point where you understand, oh, so my program is using syscalls plenty, probably. Like whenever you do network, when you reach the network, there's a syscall, typing, syscall. It's like everything, each file, so on, plenty. This is a way how you can actually debug stuff. Like you can observe what the program does without actually knowing what's inside, but just watching like what system calls it does. So you see like what files it opens, what network traffic it induces, and so on. There's plenty of options, and I guess the simplest is you do strace, and you have a program. If you want to filter just one, for example, to see what reads or writes it does, you just do -trace and cool, or you can say network and all the network stuff, and you filter things. The output from the example looks like this. It's abbreviated. There's like way more, right? But you can see the line right, 1. That's the output, right? So yes, thank you very much. Right, and it actually tells you like, hey, it actually printed 20 bytes. So cool. Then, so how many syscalls were there? That's another way how you can do strace -c, and you see these are the ones 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Was it like 16 or 17, right? Not hundreds, but it's way more. And you see like how much time and so on was left there. Most of it is actually the runtime, the Go runtime, but there are parts like the write that was definitely my code doing it, close as well. So, cool. Now, why is it important for containers? Is because containers are processes, so container runtime, so whatever, you need to somehow execute a program, mount stuff, modify things, and so on. So, one way where there's a lot of interaction with the operating system is executing other programs, which containers do, right? This is, you can say like, hey, I'm going to use syscall, I'm going to be fine. You can. It has issues though, because if you, for example, use syscall exec, it actually replaces the process you're running. So whatever is after the line exec, you'll never see this. It never gets executed. because that disappears, because your program will be replaced with the other one, right? So this is how it looks, right? I was just like, oh, I'm gonna list what is on the root, and the part never prints is never there. The right thing is actually in Go, you can do way better, and that's using the OS exec package, right? Where you create the command, then you have this std out, std error. That's where you want to actually say like, oh, std out goes to std out, and you copy over the stuff. You prepare the environment, then you run, and then when that finishes, you come back. There's a lot of tricks how to do this. If you want to do it, it would involve a lot of code to actually get it right. So definitely, this is the way to go. And the result here is, hey, command finished successfully. So you get to see your actually, it was a different process running. Cool. So I think we have all the basics. We know how to run processes and we know how to contain them, right? So, this is yours.
Just so we understand my excitement, we thought we had an hour for this talk, and I was looking at Vilda for the past 15 minutes to already, let me speak a little bit. So I'm going to try to take it a little bit faster. I apologize. There is a repository in my GitHub living in a container. So feel free to check it out, and the repository itself contains a Vagrant file that you can use to spin up your virtual machine. I highly recommend when you're experimenting with stuff to virtualize before you go and break things, own experience. There's also code that I started with, and the final code that contains all the features that we used for containing our process. Just a call out, what I will be showing here is not a full-fledged container. So firstly, do not use this in production. This is a no-brainer, but I still feel the need to mention it. Do not generally use random people's talks, GitHub repositories to run code in production. That's probably a good advice. And whatever we're gonna be doing here is just to spark your curiosity, because it definitely sparked mine. So it's not fully contained, it's not a full-fledged container. If you want to use something in production, I recommend going for the stuff that's already out there, had been developed for years by hundreds or thousands of people. Before I go a bit further, I want to mention all the people whose code I stole for this. First of all, there's Liz Rice. If you haven't heard of this lady, she's a fantastic speaker and an engineer. She has a bunch of keynotes and talks and code available. So parts of the code that I will be showing, I shamelessly stole. There's also Vilda's page on Linux containers from scratch, 7 years old, if I'm not mistaken. Vilda was very curious, always. And of course, man pages, fantastic bedtime reading. So this is what we're going to do. We are going to have a process first that is uncontained completely, and we are going to fool it into thinking that it has its own host name, its own file system, its own process ID table. It will think it runs as root, but it will run as a non-privileged user on the host, and we will limit its resources. So first thing that we're going to use is a kernel feature called namespaces. There are 8 of them. What they essentially let you do is there's some global resources each of these type of namespaces govern. And for a process, for a group of processes, you can essentially create an instance of that particular type, so that that group of processes can update, adjust, configure that resource without the rest of the processes on the system knowing about this. So, and this is, for instance, the UTS, Unix Time System. Unix Time System namespace governs the host name and the domain name. So the process can change its own host name, but it will not affect the rest of the processes on the system unless they share the same namespace. So each of the processes in the Linux system belongs to an instance of the namespace type. So you would always have namespaces. Sorry, I need to breathe as well. You would always have namespaces in the proc directory. for each of the process. The PID is the process ID, so proc directory is your friend with a bunch of useful information. And when you're creating a namespace, essentially when you're running a child process of the current process that you're in, you can set the child process to run in its own new instance of the namespace. And if you don't set this, it will run in the namespace of the parent process. The way the individual namespaces behave might differ based on the global resource that they govern. So sometimes they start with a clean slate, like the Pit namespace. They would start with a clean Pit table, and they will be somehow mapped to the parent process. Or they start with a copy of whatever the parent had. So that's the case for the mount namespace. 3 syscalls: clone, set ns, and unshare. Clone is used when you're creating a child process. You can set clone flags to indicate whether you want the child process to have their own namespace created, or whether if you do not specify the clone flag, it will inherit those from the parent process. Set ns is used for when you have an existing process and you can set that particular namespace instance to some other. And unshare is when you... I forgot what unshare is.
It actually means that from that point on you want to create a new one.
All right. So in that process, in the running process, you indicate that you want to start to use a new instance of a particular namespace. That's it. Right. So this is a bit of a nightmare. But essentially, we have a function that spawns the host process, in which we're going to use to set the context for the child process that will be our container. And then we have a function, thank you, Vilda, and then we have a function container that, that spins up that container. It will run the command that we set. However, it will also eventually specify some configuration within those global resources that I was talking about. There is a bit of a trickery there in the host process. It executes a command from the path proc self-exe, which is the binary, which is whatever is the executable of the current process. So in case you run go run file, it will an executable will be compiled and put somewhere in some temporary path, and proc self-exe will contain that path to that executable, so it can execute itself with some different parameters. The rest of the parameters in the exec command are the parameters from the shell that we provided outside of the go run file path, and yeah, that's that. There is also that I'm not showing here. The entry point basically contains a switch depending on the first parameter that we provided. So there will be either run, which will execute the host function, or container, which will execute the container function. This way we achieve that we have a parent process that spawns a child process with all the settings, all the context settings that we need. So this is how it looks like when we run it. We run a go run file path, and then we provide the arguments to the command. So run, echo hello. So we're essentially saying execute echo hello in a container. So we also have some log lines to know what happened. It goes, runs the host function, runs the container function, executes echo hello, which outputs the hello, ends the process, we're done. The second one is a bit more interesting. In the argument, we provide bin bash, so it starts a shell. So I will show you the tree. The host function executes, the container function executes, bin bash executes, so the shell is created, and we are in a container. Even though we don't necessarily know it, we're not in a container. We're in a different process on the same host that is completely uncontained. So there's a command hostname, just to show, because we will be setting a hostname first. It outputs Ubuntu. There is a command exit so that we get out of it. Looks still the same. Very confusing. this is how the process tree looks like. The PS has a fantastic argument F, forest, and it shows you the hierarchy of the processes. So this was extremely helpful to me as I was getting lost in understanding the namespaces and trying to spawn child processes, and got into some horrible deep parts. I could get out of them very easily using this command. So first step of separation, as I mentioned, the global resources. The UTS namespace specifically governs the host name. So what we can do, we can specify a clone flag here within thank you, Hilda, within the host function, and we are specifying clone new UTS, which means that this process will run with a new instance of a UTS namespace, which allows us in the container function to set the host name, which will become container, but within only within that process itself. So this is how it works. On the top side, on the top you have executing, getting inside of the container. You can already see the host name in here in the user string, but if we type host name, we receive container. Whereas in the host, outside of all this process, it is still Ubuntu. So this is our separation. The container thinks it's fine. The host is still okay. Next, we have a mount namespace. So we're going to start, we can just stack the flags this way, and we're going to start the container just to show what happened. This is the second example of the namespace behavior that I mentioned. If you create a new mount namespace, it will start off with a copy of the parent. And there are some more intricacies in the mount namespace man page. I recommend reading it several times. We are essentially starting with a copy. There are some limitations to the child process. So to further containerize, we need to point our process to a different file system. So in the Vagrant file that I mentioned, it will also download a root file system from the Ubuntu page and untar it to this path. So when you run it, you can actually, it will work right away. And we are using change root to point the child process at this particular path. Now what happens if we just run this? It will start complaining. It will complain that the current directory is weird. So something else that we need to do, we need to change directory to that new root that we just pointed the process at. And this works. It also nicely enables us to distinguish that we're running inside of a container and that we're running in a host with the colors there. You might never see root green in any other slide, but I wanted to just distinguish that we essentially have two different contexts here. This is because we pointed the container at a different file system with a different home, with a different bash RC, so I just updated that to be green. I also added a file called container in the root path so that we can see right away if we type ls that we are inside of this file system. Now, if I want to look at the processes, use PS, one of my favorite tools, it will complain that it's not mounted. So the next thing we will update in our container function is we will mount the proc file system, which is a pseudo file system that gets filled with very interesting kernel data. And among other things, you can see the values of environment variables in processes, for instance. So this is a good reminder not to store anything too interesting in them. If I type mount, it will actually show me the list of mounts. So we essentially got rid of the host mount points this way. Now, if I go for PS, if I look at the processes, it still shows, it works, which is fine, but it still shows me the processes of the entire host, so not contained. We are going to instruct the child process to run in its own PID namespace, process ID namespace, and that one starts with a clean slate, which means when you run a process in a new PID namespace, that process will have a PID 1, and it will get mapped to the parent. There's a mapping in between the parent and the container. So you can still look up the process on the parent, and it will run with a different ID. But within the container, or within that namespace, the IDs will be different. Now, I will fool the container to think that it's running as root, but it really will be running with an unprivileged user. For that, there's a new user namespace flag. With that, you need to provide some mapping so that it knows what user of the parent process to map to the user of the container process. So within the container, we will have root still, user 0, but on the host, it will be mapped to the user 1000 vagrant in this case. So if I run this, just to show each of the process in the proc directory, you can find this mapping. So you can find this within the container, and you can find this on the host. And how this looks like, on the top, you have the container, claims that it's running with root. On the bottom, you have the view from the host, and the processes that are marked there, that Vilda was just pointing to, are actually running with an unprivileged user. So this is a fantastic way of containing, and definitely a necessary one. Now, I was using change root, and this is an easy way to show how you point process to a particular file system. But in reality, in the container world, what is being used is the pivot root function, which if you read the man page of change root, it explicitly states that this is not meant to be used for security purposes. So it just points the new process at some path on the host, but it doesn't actually change anything. And if the process runs with a privileged enough user, it can break out of the change root and do malicious stuff. So pivot root is slightly more difficult to configure, but it essentially introduces a new file system, and there's no breaking out because the upper level is undefined. So this was just a note. This is how it looks like on the host if you run the process with the change root, and if you run the process with pivot root. Again, my favorite directory proc, it will show you a link to the root path. Another feature outside of namespaces, you might have noticed 8 namespaces, only use 4 of them. So as I mentioned, not fully contained. There's still a lot of things that container would be sharing with the host and with the parent processes. Another feature is control groups. These, again, there are some finite resources, more or less, that the control groups enable you to configure for a process. You might notice that there are 2 different versions, V1 and V2. Essentially, V2 was a re-implementation of V1. From what I was reading, V1 was a patchwork of different functionalities. The individual controllers were behaving differently, and it was inconsistent. Also, adding a process to a particular C group was more cumbersome. So C group. Oh, sorry. Thank you. C groups. Yes. So C groups V2 were meant as an optimization of this process. You can find the configuration of C groups in the sysfs C group directory. It's a pseudo file system, and all you really need to do to create a new C group is to create a subdirectory in that particular path. Kernel will fill out the configuration files for the individual resources that that particular C group can control, and to add the process into the C group, you would just update the file C group PIDs. Yep, this is what we're doing, our C group procs. the Go code there, and there's an argument in the PS output format that lets you display the C group into which the process belongs to. And I also found some nice tooling around C groups, systemd CGLS and systemd CGTop that lets you display the list of C groups. Now, to verify our containment, there's a couple of options out there. You can look for the different exploits that are available. This particular exploit is actually pointing at saturating the process ID table or the resources, whichever comes first. Essentially, this is a fork bomb. To protect the container against a fork bomb, all we need to do is limit its PID list to 20 in this case, which means that even if we run this within the container, that container will not have a great time, but the host and whatever other processes are running on the host are going to be fine. And that's it. Are we good?
Yes.
Thank you.